Yes, good day, students. We are starting with the topic in chemistry today, equilibrium. So a lot of people make mistake, even in some textbooks, to call it chemical equilibrium. It's not chemical equilibrium. Chemical equilibrium comes under equilibrium. It's one of the types of equilibrium we have. There are 4 types of equilibrium. One of them is chemical equilibrium. Now, also in your physics, you also do a topic called equilibrium of forces. So equilibrium means equilibrium. Equilibrium is the state of a system when there is no observable change in the properties of the system. There is no observable change. The properties of the system remains constant. The property does not change. It remains constant. You have seen this a particular jamway we have in school. We call it seesaw. That has a fulcrum here, right? So if we call it balanced seesaw, if it is balanced, even in physics, when we are doing the equilibrium of forces in physics, if you locate the center of what? Gravity with your knife edge, you will notice that the weight here is at equilibrium with the weight here, Abi. Then what happens to the meter rule? It is at a what? Equilibrium. There is no change in the property. Am I talking to you?
Yes, sir.
The mass here and the mass here are at equilibrium. So there is no change. That's what we call equilibrium. A state of a system when there is no what? Observable change. There's no change in the properties of that system. We say that system is at equilibrium. Now let's look at the types of equilibrium we have. Types of equilibrium. Types of equilibrium. There are 4 types. There are 4 types. 4 types of equilibrium. These are, the first one is called physical equilibrium. Physical equilibrium. The second one is called chemical equilibrium. The third one is called static equilibrium. The fourth one is called dynamic equilibrium. So we are going to take this one after the other. In page 2, we are going to start with physical equilibrium. Now, we're talking about physical equilibrium. We are talking about a system. We are talking about the state of a system when there is no when there is no observable change in the property of a system in which no new substances are formed. You know, it's just like we are saying physical change. A physical change is a change in which no new substances are formed and it is easily reversible. Are we together? So now, physical equilibrium is the state of a system in which there is no observable change in the properties of the system, and there is no new substance. this salt, that makes it a physical equilibrium. The reactant and the product are the same thing. Let's look at examples of physical equilibrium. Examples of physical equilibrium. First one, I want to talk about resonance. Resonance in benzene structure. Benzene structure. According to Kekulé, Auguste Kekulé concept. According to Auguste Kekulé concept. Now, benzene structure. We can have a structure of benzene like this. I can put a double bond here, single bond, double bond, single bond, double bond. I can add another benzene molecule like this. Look at this one now. Here, I refuse to put bond here. Here now, this is where I put bond here. The bond can shift here. There's a single bond here, a double bond here, a single bond here, a double bond here. You can see this is both of them. This benzene and this benzene, they are the same thing. There is no new substance. Both the reactant and the product are the same. That's a physical equilibrium. We have as many. Let's look at another example. Another example, number 2, is the balanced seesaw. Balanced seesaw. Balanced seesaw. Balanced seesaw. When you have something like this, you have a fulcrum here, and the weight here is equal, balances the weight here. It's not moving. So this is a balanced seesaw. No new substance is formed. Another example of physical equilibrium is equilibrium between dissolved solutes and undissolved solutes of a saturated solution. You can represent that with this. For example, sodium chloride, solid, forming sodium chloride aqueous. Now, in this place now, so solubility is now solubility is now at equilibrium with crystallization. What do I mean? What in the first place? What is a saturated solution? A saturated solution is a solution that contains as much as the amount of the solute it can dissolve at that temperature in the presence of undissolved solute. For example, you want to prepare a saturated solution of sodium chloride, that's your common salt. When you get a beaker of water and you begin to add the common salt inside, as you are adding it, as at the time the solution is not yet saturated means it is not full. It is not totally filled up with the maximum amount of the solute it can take. It will still continue to swallow the sodium chloride you are pouring. It will be pouring. It will be swallowing it. So the sodium chloride will be dissolving inside the water. It will be dissolving. A time is taken when the water has taken more than it has taken enough. There's a certain amount that it will not start rejecting any further one you are adding. At that time now, the solution is now what? Saturated. So when we say a saturated solution is a solution that contains the maximum amount of solute it can dissolve at that temperature in the presence of undissolved solute. So what makes you know that the solution is saturated when you begin to add solute to the water is that it starts rejecting. You now start having what? Undissolved solute. But as at that time, you will not see, but something is happening. Something is happening. The undissolved solutes are solid. They are this solid. They are this solid. While the dissolved solute, they are these aqueous that are already inside the water. After some time, you will not see it. Those ones that are dissolved before, they will come out. They will crystallize out to form undissolved solutes. While the undissolved solute will now have room to dissolve and form the aqueous solution. So they will not be going. The one that dissolved before will come out for the undissolved to go inside. But you will not see it. You will not see that a change. That's why it is equilibrium. You will not notice that change. That change is happening, but it's not noticeable. It's not observable. Am I talking to you? The undissolved solute will dissolve, while the dissolved one will come out to give chance for the undissolved to go inside. Am I talking to you now? So equilibrium has now been established between the what? Between the solid and the what? The aqueous. So now the undissolved solute now goes into the solution. While the dissolved solute crystallize out of the solution. Repeatedly, to continue like that. But you will not observe it. Because it is not observable, that is what makes it what? Equilibrium. There is a statement that is not observable change. There may be change, but it's not observable. That is that. Now, then these are examples of physical equilibrium where there is no new substance is formed. No new substance is formed. Then let's look at chemical equilibrium. Chemical equilibrium. Chemical equilibrium. This is the state of a system where there is no observable change in the properties of the system, but new substances are formed, or a new substance, but a new substance is formed. The reactant is different from the what? From the product. New substance is formed. Let's look at the examples. Examples of chemical equilibrium are: number one, Haber process. Haber process is the industrial preparation of ammonia from its elements. Industrial preparation of ammonia from its elements. What are the elements? Nitrogen gas combines with hydrogen gas to form ammonia, NH3, aqueous. So we put 2 here, we put 3 here. So you can see that the reactant is different from the products. The reactant contains nitrogen combined with hydrogen to form ammonia. After some time, in the same container, the ammonia breaks again, form the nitrogen. This one form this one, this one form this one, this one form this one, this one form this one. Am I talking to you? Yeah? So like that is equilibrium. That is a chemical equilibrium. Because the reactants are different from the products. New substances have been what? Have been formed. So it's an example. Another example is contact process. Contact process. That will be number 2. Number 2, we have contact process. Contact process is a step in the preparation of tetraoxosulfacic acid industrially, and it involves the reaction between sulfur 4 oxide SO2 gas and oxygen gas, then to form SO3, that is sulfur 6 oxide. So you can see here the reactants are quite different from the what? Product. New substances are what? Formed. So in this place now, sulfur 4 oxide is combining with oxygen to form sulfur 6 oxide. Sulfur 6 oxide is breaking down to form sulfur 4 oxide and oxygen. So, and the thing will continue like that repeatedly like that. Now let's look at static equilibrium. Static equilibrium. Static equilibrium. When you say something is static, it's not moving. So this is the state of a system when there is no observable change in the properties of the system, and there is no noticeable movements of the property of the system. That is what makes it static. Now, normally equilibrium is a state of a system when there is no observable change in the properties of the system. But at this time, there is no noticeable movement. Nothing is moving. A good example of this, an example of static equilibrium is the equilibrium exhibited in balanced seesaw. Balanced seesaw. The seesaw is balanced. There is a difference between balanced seesaw and unbalanced seesaw. When I say balanced, there is no movement. At this point, if this weight is bigger than this weight, what happens? The thing will move like this. Then there is a movement. Are we there? Then if this one is not heavier, it goes like this again. Then there's a movement. But by the time it is balanced, the force here is equal to the force here. Then there is no what? Movement. That is an example of what? Static equilibrium. Now finally, let's look at the other one, which is dynamic equilibrium. Opposite of static is what? Dynamic movement. So let's look at dynamic equilibrium. Dynamic equilibrium. This is a state of a system. A state of a system where there is no observable change in the properties of the system. And there is notably movements in the system. All the examples are equilibrium between dissolved and undissolved solute of a saturated solution. So we have said it the other time, NaCl solid forms NaCl aqueous. So in this place, there is movement because the sodium chloride solid moves to dissolve inside the solution, while the dissolved solute crystallizes out. So there is movement between the dissolved and the undissolved. That makes it the dynamic equilibrium. There is movement. So that is dynamic equilibrium. Now, and so on and so forth. So let's now look at factors. Before we look at that factors, let's look at the conditions for equilibrium. Conditions for equilibrium. Conditions for equilibrium. Number one, especially in a chemical system, the condition for equilibrium. Number one, for equilibrium to be established in a system, the system must be a reversible system. Must be a what? The system must be reversible. What do I mean? What is a reversible reaction? Now, a reversible reaction is a reaction that occurs in both forward and backward direction. Reaction that occurs in both what? Forward and backward reaction. We are giving examples before, but we are still going to give it. Like in other process that we mentioned, nitrogen gas is reacting with hydrogen gas reversibly to form ammonia, NH3 gas. Now, this reaction now can be split into two. The above reaction equation can be split into two parts. The first one is forward reaction. The forward reaction now is what? N2 gas plus what? 3H2 gas equals to 2NH3 gas. This is the forward reaction. Number two is backward reaction. Backward reaction. Now, the backward reaction will now be 2NH3 giving us N2 gas plus what? 3H2 gas. Look at this. Any confusion here? This is forward reaction. And in the forward reaction, the reactant is what? Nitrogen plus hydrogen. While the product is what? Ammonia. This is forward, moving forward. Then if we are to move backward now, this one now becomes the reactant. Am I talking? And why this one now becomes the what? The product. Because this one will now break down again to form this and this. Are we together now? So this is forward reaction, which is this. the backward reaction now, what was the product of the forward reaction will now become the reactant. And what was the reactant now become the product of the what? The backward reaction. Am I talking to you? So for a system to be at equilibrium, it must occur in reversible reaction. And this reversible reaction is often time represented with this type of arrow. Forward arrow and backward arrow. The upper one means the forward reaction, while the backward, the one down, look at the mouth, look at the direction, is backward reaction. The first one that is up, look at the bottom, it means the reaction is starting from this place, reactant. Then look at the point of the arrow, that is the product. But this one now, the bottom is pointing to the reactant, while the head is pointing to the what? To the product. Am I talking to you now? Then another factor, another condition is that the rate of forward reaction, must be equal to the rate of what?